Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. When we look at the masterpieces of the Dutch Golden Age, particularly the works of Johannes Vermeer, we are often struck by a very specific, almost ethereal quality of light. It is a soft, diffused, and slightly milky illumination that seems to wash over his subjects, from the famous girl with a pearl earring to the humble milkmaid. For centuries, art historians attributed this to Vermeer's unparalleled genius or perhaps his use of a camera obscura. However, modern geologists and atmospheric scientists are offering a different, much more explosive explanation. They believe that the atmosphere of the 17th century was fundamentally altered by a series of massive volcanic eruptions, which dictated not only the light available to these artists but also the very density and composition of the pigments they used to capture it. To understand the Vermeer Sky, we have to look at the global climate of the 1600s, a period often referred to as the Little Ice Age. While political and religious wars were reshaping Europe, the planet itself was undergoing a cooling phase. A major driver of this cooling was volcanic activity. In the year 1600, the Mount Huaynaputina eruption in Peru sent staggering amounts of sulfur dioxide into the stratosphere. This was followed by several other significant eruptions throughout the century, including Mount Parker in 1641. When sulfur dioxide reaches the stratosphere, it reacts with water vapor to form tiny sulfate aerosols. These particles act like billions of microscopic mirrors, reflecting sunlight back into space and cooling the Earth's surface. But they do something else as well. They change the way light moves through our atmosphere. Normally, the sky appears blue due to Rayleigh scattering, where shorter wavelengths of light are scattered more easily by small gas molecules. However, the larger sulfate particles from volcanic eruptions cause what is known as Mie scattering. This process scatters all wavelengths of visible light more uniformly, leading to a hazy, whitened sky during the day and incredibly vibrant, fiery red sunsets. For a painter in the Netherlands, a country already known for its high humidity and coastal mists, these volcanic aerosols intensified the atmospheric diffusion. The Dutch light wasn't just a poetic myth, it was a geochemically altered reality. The sky was literally a different color than it is today. This environmental shift had a direct impact on the technical execution of Dutch paintings. Because the light was more diffused and had a lower contrast, artists like Vermeer had to adapt their painting techniques. To replicate this milky light, they began using specific pigment densities. Vermeer, in particular, was known for his lavish use of high-quality lead white and natural ultramarine. By layering these pigments in varying densities, he was able to simulate the way volcanic light filtered through a lead-paned window. The high density of lead white provided the necessary opacity to represent the bright, scattered light, while the translucency of his glazes mimicked the atmospheric haze. Furthermore, the volcanic eruptions affected the availability and cost of pigments. The cooling climate disrupted trade routes and changed the chemical yield of certain minerals. For instance, the production of smalt, a blue pigment made from cobalt glass, was a staple of Dutch landscapes. The specific chemical impurities found in 17th-century smalt often reflect the environmental conditions of the time. Scientists using X-ray fluorescence and electron microscopy have found that the Vermeer Sky, in many paintings, contains a unique density of particulate matter in the paint layers, which some believe was a conscious effort to match the higher optical thickness of the smog-filled, post-volcanic air. Landscape painters like Jacob van Ruisdael also documented this phenomenon. His famous The Bleaching Fields at Haarlem shows massive, towering clouds that seem to weigh heavy with moisture and particulate. These weren't just artistic dramatizations, they were accurate observations of a sky loaded with volcanic ash and aerosols. The muted palettes and silvery tones that became the hallmark of 17th century Dutch art were, in many ways, a record of a planet in the midst of a geological crisis. The light was colder, the shadows were softer, and the air was physically thicker with the remnants of eruptions from half a world away. When we analyze the Vermeer Sky today, we aren't just looking at art. We are looking at an accidental climate archive. Each brushstroke captures a moment when geology and human expression collided. The density of the pigments used by the Dutch masters serves as a proxy for the optical depth of the 17th century atmosphere. It reminds us that even the most secluded artist's studio is never truly isolated from the vast, interconnected systems of our planet. The next time you see a Vermeer, look closely at the light. You aren't just seeing the genius of a man. You're seeing the afterglow of a volcano. For more incredible facts like this, don't forget to subscribe and turn on notifications.